Hey, John here. Let's talk about these things. These are SD cards. This is the original SD card, the standard SD card. This is a micro SD card from Micro Center. Perfect place to buy one, I guess. There's also a mini SD card. I don't happen to have any. All right, show you one of those. I'm sure there is a Wikipedia page somewhere dedicated to the mini SD card if you want to know more about that. Now, on the original Z80 Retro project that I'm working on, I wanted to use this card size, but it turns out the connector, as you can, I mean, this card's like more than 4 times bigger than this than the micro over here. It's so big, there's no room for it on the circuit board. And once again, the cost of real estate rules out my first choice. Okay, so that's gone. That leaves us with a micro SD card. The necessary evil to shrink down, right? It's not too bad. The big difference between using the small one versus the big one has to do with how hard it is to solder the little connector on. Pins are just closer together. But once you get over that, there's really no difference at all. The software will work either way. Feel free to hack up the design and put the big one back on if you want to, or use the adapter off to the side and an external board if you want to. Okay, so that then leaves us with how do we get files on this card so we can plug it into the retro board, right? Now, some laptops and PCs actually just have slots. You can plug them right in. Other ones don't. Raspberry Pis, for example, don't. Yes, they do have an SD card slot, but it's used for the file system it's running on. So you don't really want to pull that out and try and use that to format this one, okay? So you can buy these adapters. This thing I got on Amazon, it's probably just the cheapest one I could find. It has a USB-C on this end over here and an A on this end over there, so I can plug it into just about anything. And I'm going to plug it into my Raspberry Pi. On the sides, you can see it as an SD slot, a regular SD on this side and a micro SD on this side. So you can just plug your card in like so, right? And you're in business. Plop that baby into the Raspberry Pi, and you can read it and write it to your heart's content. Okay, so here's my Z80 Retro rig with the flash programmer plugged into my Raspberry Pi. And just so we're all clear, this Raspberry Pi is configured exactly as I outlined in my video on how to configure my Raspberry Pi. And I point that out because if yours doesn't act and work quite like mine is right here, at least you know exactly how I set mine up, and you can figure out what's the different settings you might have done with yours, okay? So I got my little adapter. I'm going to go ahead and plug it in as one of the USB ports on the Raspberry Pi. And now we can just use regular Linux command line tools to tinker around with this SD card and do anything we want with it. Lo and behold, there is an SD card Wikipedia page. And yes, it does mention the mini, which I've never seen. Anybody ever use one of these? Let me know. I honestly, I'm not just fishing for comments like every other video. I've never actually seen one of these. What devices actually use these things? Suppose I could Google that after this and find out more about that. But whatever. If you've ever used one of these, let me know. I gotta wonder. Maybe that was a half-baked attempt at shrinking down because everything I know today uses these micro ones. So what does SD stand for, right? It stands for Secure Digital. This might need to be corrected a little bit. According to the specification, there's an SDSC card, which stands for standard capacity, which they don't even list here. There's a high capacity, extended capacity, and ultra capacity. Now, in my retro board project, I write a driver, and we're only going to support HC and XC cards. Those are by and far the most standard sizes you see today. This is everything from, like 2 gigabytes up to 2 terabytes. That's these class of cards here. If you go over 2 terabytes, which right now, I think I did a Google search recently, and 1 terabyte card costs you $500 today, so I don't think I'll be supporting these, and even so, the Z80 is never going to make use of that. It'll probably take 6 months for the Z80 to transfer the data at the pitifully slow rate that we are able to go. So if we scroll down through history, who did what, when, and all this other fun stuff. Ultra capacity, yay-ha, 128 terabyte limit. Wouldn't it be nice to have to outgrow that? I mean, I don't know what I would do. I have video and stuff. That's really what it's for, probably. Media. There's your SDSC designation, the original card, right? So the high capacity and the extended capacity here, these two cards work the same way when we look at the driver inside, how the software works. These standard capacity cards have a variable block size, and the protocol differs a little bit when it comes to, asking for what data you want to read and write on the card. So to keep the driver simple, and since no one uses these other the tiny ones and the gigantic ones today anyway, this is where the cheap cards are. This is the volume going on in the market right now. These two have the same protocol for transferring blocks in and out of the cards. Each block is exactly 512 bytes. And there's really no negotiating that, right? Again, you sift through the details of the specification. We are going to be operating it in SPI mode with the Z80 Retro board. So even if there is an option in the what they call SD mode, in the high-speed modes and all the other fancy, complicated things, in the SPI mode, you don't have as many options. It's very simple. 512 bytes blocks is all you have to work with, okay? And the ultra capacity, I didn't even read about this one yet. It probably allows you to simply define larger block sizes so that you can move more and more data using a very similar protocol. If you open up and read the spec, the ultra capacity is not currently supported in SPI mode at all. So the Z80 Retro board will never be able to talk to this unless they change the spec or support SPI. Now they talk about other things, the speed rating and the extra pins. I mean, these things can actually have PCI Express buses right on the cards. And they even have like an M2 version of the card. You can plug it in on your motherboard if you want to. And all this is fine and dandy for your day-to-day use, your media files and all that. But it's way more than we need to deal with on simple embedded systems like the Z80 Retro board project. So, what does all this boil down to? We're going to use HC and XC style cards. And in this configuration on SPI mode is where we're going to run it. The memory in the SD card is defined then as a series of 512 byte blocks. Each block half a K, right? The very first block on the card normally, okay, is going to be used for the thing called a master boot record. The very first block is block number 0, okay? 512 bytes for block 0, 512 bytes for block number 1, 512 for block number 2, up to block number N, where N equals, it's defined in terms of how big the card is that you bought, right? So as many blocks as you pay for, up to the capacity of the cards. These will go up to 32 gigs, and these go up to 2 terabytes, okay? Let's look at this repo here I created that holds the, this is the base where I'm going to be building my CP/M BIOS for CP/M 2.2, all right? Now, quick look at what's in here, this boot directory. Okay, this is where we're heading, all right? This is, if you open up this and look at some of the doc in here that I just tweaked, by the way, if you've been playing around with this, do a pull. I lied. I just fixed some documentation here that would be a little bit misleading, okay? What are we going to try and do, all right? This is the code that goes into the flash when we're ready to start working on CP/M. What does this do? It's going to load 16 bytes from the first blocks, however many that is, right? So that'll be 32 blocks, each of which are 512 bytes each, okay? I should have wrote 32 in there. It's going to read it on a partition number 0 off of our SD card. It's going to put it in memory starting at load base, the symbol that I define in memory.asm. And then it'll just simply assume that that's executable, and it'll jump to that address. In fact, we can probably even do a quick look at the code. We've seen this 100 times. Copy the flash memory into the SRAM, set up a stack, initialize the serial port, say hello, call a subroutine. This is going to be the boot off of the SD card subroutine. If it can't read the SD card, like there's not one plugged in or it just fails for some reason, this subroutine will return. It'll say, I can't do anything, so I'm halting, and then it goes into this spin loop here, okay? We don't need to look at every line of code down here. We'll get here soon enough, all right? So this is where we're heading. We want to load our operating system. That's what we're going to put in the 16K here. We want to put it in partition number 0, and we'll talk about that in a minute, on our SD card, and then we're going to boot from it. All right, this is basically how all operating systems ultimately boot. They need to do a kind of a two-stage boot up, right? The firmware is our first stage, and it loads code off of the SD card and then branch to it, and then it can do more as it needs, okay? Here's a little test program called Hello. This can be used as a stand-in for the CP/M operating system. So first thing we're going to do is we're going to run this program, okay? Notice it says org to load base. Again, that's defined in memory.asm. It happens to be set to hexadecimal C000, where the flash bootloader will read and load this code into, and then just branch here, right? So what am I doing in here? I'm going to print a message, all right? And then I'm going to go into a loop. All I'm going to do is print a message, wait a little while, and go back up. What am I doing? Going back up to the loop here. So this is going to run this loop indefinitely. This is some old stale code that I probably should get rid of because, as you can see, it never falls through down here. So this is a vestigial amount of stuff that has been left behind. So this is our stub. Once we can boot and run this, we're totally ready to start playing around with a real operating system. This is, in a sense, the first operating system that I'm going to boot and run off of my SD card. And it's just going to simply say, hello, 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 hello. Okay? Again, where we're going before we try to get there. This library here is where all the little driver routines are. Here's your memory.asm that gets included in there, and this is where I define load base. The idea being you only want to define things once and only once, so that when any two different systems need to agree on some value, they all get it from the same place. That way, if and when I change this and recompile everything, everything will be adjusted accordingly, and they'll all always agree with each other, okay? The rest of this stuff has to do with the CP/M image that we're going to load down the road. What else is in library? I think I actually talked about a lot of these already. The big one here is this SD card driver right here. We won't get through all of this in one shot. Right now, I just want to talk about the SD card itself. But if you want to work ahead after you watch this one, this is the next leap that we're going to take. Okay, so I go one at a time through all these routines. All this stuff is defined in the SD card specification, and I just simply implemented them based on what they said in there. All right. We also have tests. This is the SPI test app that I talked about before, and now we have an SD test app that we're going to use to exercise that SD library, okay, the same way I exercise the SPI library with this test app down here, right? And some notes on how to install them into the flash and when we're running them, all right? So today what I want to talk about is this README file right here, which is a high-level view of the SD card so we can get our bearings. Number one priority, understand the master boot record, the partitions, how they are defined, where the data is on the SD card, so that when we write our driver, we can figure out where the data blocks are, okay? I'm going to click on the README. If you read it in here, I love it when they waste a third of the screen because there's some little menu up here. In GitHub, if you click on the actual README file, then the whole page gets dedicated to the one thing, and you can embiggenate the font like this, and maybe make it easier to read in your YouTube video, especially if you're looking at it on your phone. That might be a little too big. We'll go with this one today, all right? So what is this thing doing? The website basically currently is, I document, this is a bootloader for CP/M 2x2 BIOS, okay? I'll probably update this and reorganize, refactor this README file as we go, but for now, I think this works well as a backdrop for this particular video. This link here goes to the simplified specification. They've done us the favor of breaking it down into, I don't know, a dozen files. The main one right here, part 1, is the physical layer. This is the main document right here. We don't need ultra high speed, near field, all these other things, you know, how to extend this, that, and the other thing. These are all advanced features. Bluetooth, none of this is relevant to us right now. Let's keep it simple. Grab this. If you click download, there's like a click-through license in here, and this is why I'm not going to show it, because it says you can't reproduce it, blah, 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 blah. All right? There's copies of this around the internet. I'll put a link to a website that I also looked at. There's some C code in there that looks Android-like, or and not Android, Arduino-like, I should say, that is a similar low-level driver to talk to the SD card, and you can use that as a guide if you want, beyond the assembly level stuff that I'm working at for the retro board. All right, there's a Wikipedia SPI article. I think I showed that in the SPI video. The MBR we'll see in a minute, and the SD card article that we already saw. Okay, let me show you what's in this file, and then we'll come back and look at the MBR and start playing around with the SD card. Number one most important thing to do is hurry up and void your warranty. Number one priority in all projects, right? Okay, so let's make sure we at least get there today. What do I got on here? And I mentioned that any sdaHD card should, emphasis on should, work for this project, okay? And according to the specification, and I don't have any XC cards lying around that I can test with right now, they should work as well, and I really should test it. And I will, and I'll update this accordingly when I have done that, okay? I put out that this is where I got the card, all right? I got one of these micro centers down the road from where I live, $4. If you wreck it, throw it away, okay? At this price, you can't afford not to buy one. In fact, the first one that I used, I actually broke it. It turns out these are more brittle than I thought. And at one point, I plugged it into the retro board. I don't remember what I was doing, but I was holding it upside down or trying to flip it over, and I grabbed it by the corner, and my thumb rolled off the edge of the card, because the card sticks out, remember, from underneath the Z80 Retro board. And I put a lot of pressure on here, and I just broke the whole back of the card off. All right. Now, I mention this story because you probably don't want to break yours if you only have one or two. So don't use it. No step, right? You know, when you get a lawnmower and it says don't step here, no lifting by the SD card. That sucker just snapped right off. So you don't want to do that. Anyway, so those are the ones that I'm using. If yours doesn't work, the reason is, full disclosure, right? I don't get paid for this. What do I get from these guys? What are they going to do? Give me a penny, even if there was a finder's fee on that for $4? Anyway, no, full disclosure, right? If you got a card and it doesn't work right, at least we know this one does, right? So for $4, you can solve your problem if you don't want to try and debug the code, or if you and I can't figure out how to do it. Comments below the video, or send me an email and stuff like that. We'll see if my goal is to make sure that they work, but if we get stuck, $4 will get you out of that problem, right? So let's talk about this whole partitioning thing. A lot of us probably already are aware to some degree that hard drives and large media has these so-called partition tables. And 40 years ago, they invented this thing called a master boot record that has this partition table in it, which is what we need to understand here if we want to be able to have more than one partition on a card, for example. We don't need to do this, but by doing it, I think we're better off in the long run, especially if we want it to be compatible with, like a Raspberry Pi or a Windows machine or something like that, so we can share the data on the card. Most systems expect there to be an MBR these days on media like this. Linux really doesn't care. Windows definitely would care. Anyway, so here's the deal. We'll walk through this in a minute. And I put notes in here. I need to update this. And maybe somebody, please offer comments, observations. If you want to use a GUI or something like that, you got your favorite partitioning tool, let me know. I'm going to be using a pretty primitive one that comes with Linux. And this is currently in parentheses here. What we do is we create so we segment the SD card into pieces. You know, we got a big bunch of memory. Maybe I want 4 gigabyte sections instead of one 16 gigabyte card, right? So each of those sections is what they refer to as a partition, right? And the master boot record has a table in there that defines where all the partitions are, and it defines what type of file system is in each of the partitions. I should be using type 7F. But the uber-duber primitive partitioning tool that I have doesn't let me specify this. So I'm going to lie, you'll see in a minute, and tell it it's a Linux partition. So if you plug this thing into a system that tries to be handy and helpful, it might get very confused, because we're not going to be putting Linux file systems in there. We're not going to be putting FAT file systems in there. We're not going to be putting any file system that any system would ever recognize in the partitions on this SD card, okay? We could, but if we did that, it turns out the amount of code we'd have to put in our retro board operating system to be compatible would probably be bigger than the entire operating system itself, and we wouldn't have enough memory to deal with it anyway. So we are very much in the experimental zone here, okay? A little foreshadowing here. Just be careful. Okay. And this is why. One of the problems is that CP/M disks don't have, like most modern systems, you know, you put it in there, you can actually look at the data, and they have magic numbers and signatures and things like that in their files, so that even if, you know, you don't know what they are, you can kind of open it up and give it a little sniff test on there and say, oh, this thing identifies itself through its contents rather than its name as being a whatever, an exFAT file system, or a Linux ext2, ext3, that sort of thing, all right? CP/M does not do that. Now, we can put that in there, but by their de facto standard, they don't have anything like that. So we got to be careful about this. Point is, no CP/M file system is going to be directly readable by any system. You have to tell it by hard coding into whatever your apps are. Yeah, I know there's some M tools and things else that, like that out there, but none of them will work by just analyzing the file system and then, and I'm air quoting here in the studio, they won't do the right thing because they can't know. All right? So be very careful about trying to be using overly helpful tools. All right? Just a little warning there, okay? So what am I going to do here? I'm going to create a disk for hacking purposes, right? What are we going to do? It would be nice to be able to create a partition and make it 7Fs. If it's experimental, then you're really disclosing to the host operating system on your Pi or your Windows box or whatever to just say, hands off, don't try to help me with this because it'll get messed up. Now, what I'm going to do is I'm going to create 128 megabyte, the little I don't know why everybody changed the way we do this, and I'm mixed bag in a lot of my documentation these days. The little I means that this is in binary. So 128 in binary is really like rounded off to decimal. We call it 128, but it's really actually more than that. It's this much, okay? Why did I do that? I want to be able to create one partition on the SD card ultimately. And in there, we can then hold 16 8 megabyte disks. Why would we want to do that? Well, the maximum number of disks by default on CP/M systems is 16. And the maximum size of any disk is 8 meg. So, if we create a 128 megabyte partition on our SD card, inside there could be what CP/M sees as disk A, disk B, disk C, disk D, and so on. And it would see 16 8 megabyte drives there, okay? It's not obvious how to do this when using a simple partition editor, okay, like the one we're going to see. So just, again, foreshadowing. You know, some of this is hand-waving when it comes to, it would be nice to be able to do this, but the partition editor that I have doesn't give us a way to do that easily. Now, we can write a simple program that'll just simply write out the partition table and create an MBR. It's real easy to do. We'll look at it in Wikipedia in a second here, all right? So why am I on about all this stuff, right? We're going to ignore the partition type. We're going to mark it as being inactive. So if you plug this in, no operating system is going to try and mount it and try and help you, or think for 1 minute that it really is a Linux-based file system that we're going to end up declaring it as when we create it above here, okay? Now, one last thing. Danger, Will Robinson. This this absolutely will cause catastrophic data loss to the entire SD card. That's true. But if you don't do this right, you can lose every bit of data on your entire system, okay? Don't come crying to me if you just cut and paste a bunch of stuff off this web page. You have been warned. You need to be very careful about this. Do not do this for your first time on your desktop daily driver if you're running Linux on there. You probably will erase your boot drive and get very angry, okay? If you do what I have in here on a Raspberry Pi, which is what I'm going to show you in a minute, these commands will work. They'll work just like this, just like the one that I just plugged in on my workbench. It'll be fine. And even if it's not and you screw it up, what will you have lost? A half an hour to recreate the SD card in your Raspberry Pi and try again, okay? Don't do this on your desktop, okay? I should have like a Batman flying bat warning thingy in here. I don't know. Anyway, okay, so what are we going to do? First thing we're going to do is void our warranty. Let's get on with it. Erase your SD card. Why do we want to do this? We want to get rid of any existing master boot record. Again, we'll talk about that in a second. When you buy an SD card, according to the specification, there will be, FAT file systems of some time, exFAT, vFAT, whatever, on the SD card. Now, the Raspberry Pi that I've configured will not help us, will not help you. By trying to mount it and be helpful. Oh, I see you put an SD card in there. I'm going to mount it and make it available for you. We don't want that right now, okay? When you build a Raspberry Pi and you do not turn on or install or enable the full desktop GUI, environment in there, it won't be helpful. When you plug in an SD card, it'll just say, oh, look, somebody plugged in an SD card. That's nice, and it won't do anything with it. That's what we want right now, because we're going to manually manipulate this thing. Again, I configured my Raspberry Pi, and there's a whole video on it. If you do it the same way, you won't have that weirdness going on. It won't be overly helpful. It'll work as I show here. Okay, so the first thing we want to do is take the factory stuff that's in there, which if you've ever used a USB drive or an SD card before, it would come pre-formatted with some sort of a FAT file system and no files or some advertising that you never want to see anyway. And what we're going to do is we're going to write binary zeros into that card. We're literally going to save. As you can see, this is block size 512. We're going to create all binary zeros. That's what dev0 does. It's an infinite supply of binary zeros that, and this runs on the Raspberry Pi, Linux, any Unix system has this, okay? We're going to write 10 blocks, each of which are 512 bytes, into dev SDA, okay? Now, what we're going to do here and demonstrate is how we manipulate the drive itself. Now, if we go over to a Raspberry Pi window, and you look at dev and SD, this is where all the device nodes are. And if I just simply say list every device that starts with SD, all right, you'll see SDA sitting in here. It might say SDA, it might also say SDA1, SDA2, SDA3, and so on, all right? The reason this currently only says SDA is because I already did a test drive of the demo I'm going to show you in a second to make sure everything's working here. And we'll see it show up with extra SDAs in a minute, and I'll explain why. But my point is, you might see extra ones in here. That's okay. So come over here and grab this line. Now remember, we're going to destroy everything on this dev SDA drive by doing this. I'm back on my Raspberry Pi. It says Raspberry Pi right here. I think I say it out loud. I say it in my head. I'm not on my desktop system. Why? Because if I do this on my desktop system and I sudo to root and I do this, I will blow away everything I've been working on for the last year, which is on my system. Yes, I have backups, but I do not want to rebuild my entire desktop. Okay? So on my Raspberry Pi, I'm going to write 10 blocks of all binary zeros into the SD card. As you can see, it finishes instantaneously, practically. And now I've destroyed the contents on that SD card. In theory, you could recover it if you spent a huge amount of time. Just don't. Okay. By writing zeros in there, I have, at a minimum, destroyed the master boot record that's on that SD card. Okay? And I want to do that because I don't want any creativity showing up in here. As we move forward, it's absolutely critical because I have hard-coded inside my first draft of my BIOS exactly where the partition is on the SD card, and it has to match exactly this right here. All right? Yes, it's lame, and we should discuss the best way to improve that code so it can self-configure in case you want to partition it in some other way. For now, do it like this so that we all meet at the end when we boot up our Hello World, the first draft of the BIOS. All right, so before we blindly start playing around with the partition table, let's go in here, because the MBR holds the partition table. If you read this Wikipedia page, it'll go on and say, this is the special boot sector at the very beginning of a partitioned computer, and blah, 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 blah. This is the stuff that's in the actual block number 0 on your SD card in most hard drives. Now, keep in mind, this is only one way to do this. Most systems today are fully compatible with this exact format that we're talking about, and any Linux system certainly is, and any Windows system certainly is. I'm also certain that any Mac would be, but I don't have direct experience with that, okay? Why? Because it's been around for 40 years. It's entrenched. There's other and there's newer formats. In fact, even the MBR has got some variations in it. Let's take a look and see where we're heading here, okay? So it gives you the eyeball view here. When you have a hard drive, sometimes they're really big and you want to break it into pieces. I can create more than one bootable partition, as we will see, on one media. So this is, if I'm dual booting my system. Well, this is one way to do it. You can either have two different drives. You can have one drive and break it into two halves, two partitions, and you can boot off of one partition or another, okay? And that's what this is all about. Now, this font is got this thing kind of screwy with its indentations here. Let me zoom out a little bit. Maybe I can get this to come out right. This is actually kind of hard for me to read. I'm going to zoom back in and say I don't care. This is the generic MBR, and this is critical we understand, right? This is user-defined. I can put anything I want in the first bytes of this block, the first 446 bytes of the 512-byte block. I can do it as I please. After that, I can create 4 entries into a table, and they call it partition entry 1, 2, and 3, 4. I call it 0, 1, 2, and 3. I apologize. Maybe I could change my doc back again. To me, it's confusing to call this one partition 1. The first one's 0. I'm not a Fortran programmer. I'm a C programmer. Anyway, this is called the partition table. Point is, the first one is the one that we care about right now, and the only one that the first draft of my bootloader code ever deals with, okay? We'll look at these entries in a second. After this 4-entry table, the last 2 bytes in the MBR, in the first block on our SD card, must be set to 55AA in order to identify the fact that we have, in fact, put an MBR in there and that these table entries are then, therefore, allegedly valid. All right? Now, I just copied all zeros into the first 10 blocks on my SD card. Therefore, there is no MBR on this card from the perspective of Linux right now, because 55AA is not there. Okay? Well, any operating system you plug that SD card into at this point in time will give you some kind of a thing. If they're in be helpful mode, it'll give you some sort of an indication that say, hey, you put a card in here that is not, partitioned. It's not initialized. There's no file systems. And usually they'll say, do you want me to create one for you? And you fill out the little answers and it'll be, set it all up however you want. Okay. Right now, this is literally blank. And this is what we need to fill in. Now, they have so there's the generic bird's eye view up there. Then they have these other things that say, well, modern days, what they really do is they put, the first 218 bytes. It actually has their boot code in here, and they put some timestamps and some other stuff in here. And then down here is your 4 partition table entries and your boot signature. Some other company does it like this, and someone else likes to do it like that, and so on. Every one of these things in common has 4 partition table entries at the bottom, okay, followed by the boot signature. Here's one that the whole thing is filled up with a bunch of partition entries, and then they have the standard 4 here. So maybe this one has extra one, expanded ones or something. All these are variations on the generic one at the top, okay? Now, down here in this website, it says, regardless of how you create this thing, if you're going to use this MBR style partitioning mechanism with the 4 entry table, these are what each of the 4 entries look like. And this is the part where we talk about the status. And when I say the status is bootable or not bootable, all right, the valid, invalid, we're going to mark this thing as invalid so that the operating system doesn't get too confused. Then what we're going to do is we're going to tell it, this is the old style, cylinder head and sector numbers. This has to do with, if it actually is a real disk and it has actual platters, which platter, which track, which concentric circular track, and which sector on a track is the beginning of the partition, okay? I don't care. I don't want to deal with this garbage. These are yesteryear, waste of time. It was a waste of time then. It's a waste of time now. The reason this was done this way was to help people optimize how their system worked. And honestly, it was probably not a bad choice 40 years ago, because what it meant was that it was easier for certain disk controllers, because you actually do need to tell the head to move to a certain track distance from the center spindle, which we call a cylinder. And we need to ask which platter, which head, which side of which platter we want to talk to, and which sector on that track we want to be reading or writing. And that was how you talk to the hard drive. So this would have made it easier, and it did, I'll admit, when you're writing low-level code for that kind of a disk controller. But over the years, it became very annoying to do things this way and caused all sorts of limitations. So what we do is we leave it in there because, if you're still running 40-year-old code, you need this. And then right next to it, you'll notice that there's a CHS, cylinder head and sector, of where the partition starts, and then another one of where it ends, okay? We'll come back to this type in a minute. That's the one where we're going to set in lie. And then after that, they just said, we give up. We'll leave that in there, but I don't care. I'm not going to use it. There's what we call the LBA of where it starts, and then there's the number of what they call sectors, okay? Their terminology are sectors for what SD cards call blocks, all right? And this terminology is going to become very annoying because CP/M has logical blocks, physical blocks, sectors, extents, and directory entries, all right? So let's be very careful that we're always remembering whose definition of sector we're talking about at any point in time. So what am I, why all this stuff? Why? Because you're going to see it, and I don't want you to get confused. I don't care about the CHS addresses. When you use a partitioning tool, it's going to put some stuff in here so that an old system that wants to think in terms of cylinder head and sector can still end up kind of figuring out where the partition really is. Okay, and it is analogous and compatible with this whole thing here, where why don't you just tell me the block number where the stinking thing starts? That's what this is. All right, the SD card block number of the first block in the partition. Can we make it easy, please? And then this one here, call me crazy, but just tell me how many blocks there are in a partition. These are what we're going to use, okay? We don't care about the cylinder heads and all this other crap. This partition type thing is the relevant part for the partitioning tool. And this is the one that tells the operating system, you know, what they can assume is in that partition. And the tool that I use, like I said, I can't just put any value in there I want, which seems odd to me. It insists that I actually pick one from their menu, or I'm wrong. Please, if I'm wrong, tell me in the comments below. We're going to go ahead and just say it's a Linux partition because that's what the editor thingy does that I'm going to use. And Linux doesn't really care as long as it's not going to get too whiny about trying to be helpful. And it won't if we mark down here the status of the partition as not being bootable. We're going to mark it inactive. Okay, and we're going to mark it as a Linux partition because that's what the editor does, and we're going to put in here where the partition starts and how many blocks. All right, so that's what and you can create 4 partitions, each one of them hopefully not overlapping with each other. Otherwise, things get very confused. And yes, you can do that if you want to create a problem. Okay, so let's now go back over here and look at what we're going to do with the partition editing tool. So what we're going to do is we're going to run a tool. We're going to say, I want to create a partition table and write an MBR onto the drive on the device called SDA. And by doing this, by specifying SDA and not specifying SDA1, SDA2, SDA3, and stuff like that, okay, SDA is the name of the entire SD card. Okay, and when you first start this, it gives you a couple of clues. Check this size. If you put a 16 gig card in there, and it's not, you know, roughly about 16 gig, it means you're probably not taking my advice, running it on maybe your daily driver, and you got the wrong drive. And as soon as you play around with this, you're going to wreck everything. So be careful. Read this thing, all right? Now, it's going to tell you that each sector is 512 bytes. Now, I'm creating an MS-DOS compatible partition style table, and that's what that thing is that we just looked at in Wikipedia. What am I going to do here? So when you run it, I'm going to say make a label. That means put an MBR in there of the MS-DOS style. And then I'm going to make a partition. And the fact that I called it primary means that it is one of the 4 entries in the MBR. In other words, it's not an extended partition, if you know what that is. Go back to the Wikipedia page, read all about those if you want to know more. Keep it simple. I want a primary partition. These numbers here say start. Unfortunately, you can't just put block numbers. Actually, maybe I can, but the way this tool works by default is these numbers are expressed in megabytes. I can't start it at megabyte number 0. Actually, I probably can, but the tool might yell at me. Because at megabyte 0 is block number 0, and that's where the MBR is. Generally speaking, you don't put the MBR inside of one of the partitions. You skip a little space, all right? You skip the MBR. So I'm going to start at megabyte number 1, and decimal 135 is one more than 134, and that is in decimal 128 megabytes for my partition size. Right? It's a little annoying that we got to do this in decimal, but so be it. I then say print right here, and this is what prints all this stuff out. Because at this point, it wrote the partition table in on the disk, and I say, okay, print out, what is it? And it'll come back and it'll tell me all this fun stuff, okay? You might want to do a print before you do this and check what it is before you wreck it, okay? I probably should update this page and give you that advice. So anyway, yeah, after you've done your damage and voided your warranty, it tells you here's what you've got. And it says, okay, it starts here, which is at 1 meg. It ends there, which is 128 meg beyond the starting address, and here is 128 megabytes expressed in decimal. primary partition, which means it's in one of the partition table entries, which is the number 1. It's the first one that I would call partition number 0. And it is an LBA entry, which is what you want, so that we can just simply read the LBA numbers and ignore all that cylinder garbage. You type quit, and you're done with the tool here. All right, so let's go ahead and run this. All right, so I'm over here on my Raspberry Pi. Oops, nothing like blindly copying things like a fool. You want to run the command, not that other thing. Okay, so here's the part editor. All right, let's go ahead and print before we wreck it. Okay, what does it say? I've got an unrecognized disk label. Perfect. Why? Because I don't have the 55AA or the AA55, whatever that is, at the end of the MBR. What it will tell me, it's a mass storage class device. Now, in Linux, they use the SCSI driver for all kinds of things, including USB drives and SD cards and stuff like that. So this is actually telling you, oh, by the way, Linux is treating this as if it's like a SCSI hard drive. It says it's a 16 gig. It's not fully 16 gig because it's going to round it down a little bit due to some housekeeping junk in there. Here's my 512 bytes. I have no idea what your partition table is or anything else because there isn't one there. Perfect. Why? Because we zeroed it out 5 minutes ago. All right, so let's go ahead and then create some. I'm going to create a label called MS-DOS, and once I've done that, I now have an MBR on the disk. There's no partition table entries in there yet, but it's legal. In fact, let's quit out of here and see what it looks like. Why? Don't do this, by the way, on a Raspberry Pi. Normally you would if you're creating a real drive and you want to mount it in Linux and stuff like that, but that's just a reminder for the normal case. We're creating a drive for a whole different purpose, so this is the abnormal case. So if you scroll down here, we can actually look and see what the MBR has in it. Let's see what's in there before we fill in the partition table, okay? So let's look at this command. What's DD? It's like a disk dump or something like that if you read the man page for it. What's it called? Okay, it doesn't actually give it much of a name. What it really is doing, this is a binary copy utility. And you can give it all kinds of commands, like every time you read or write, every time you transfer data, do it in 512-byte chunks. And do this many. Okay, this means throw away anything that DD wants to print to its error messages and stuff on the screen. And the reason I do this is because, let me show you what happens if I don't do anything else. All I'm going to do here is dump out the contents of what's on the card, okay? And then I'm going to, I got a bit of a problem now, don't I? Because what's on the card is in binary. All right, if you just do this, it'll print it on the screen, and it'll be garbage all over the place. We'll go ahead and do that, but you'll see this is not terribly useful, all right? But when DD is done, it writes, hi, I copied this many records in. That's one block. And by the way, that's 512 bytes, and it took this long, and stuff like that, all right? Now, if you run this and it prints all this junk, it's going to spew it into the hex dump routine. It'll come out on the screen and wreck my display of what's going on. So if you say to right arrow, what I'm really doing is directing what we call file descriptor number 2, which is where the error messages go, and throw them in the garbage. Dev null. It's a black hole, okay? And let's go ahead and do this. We'll add that and nothing else. Now what happens is DD will do its job, print the garbage all over the screen, and it still wants to print all this stuff out, but I throw it away by putting it into dev null. Let's see if there's a command line option to tell it to shut up and not say anything. None suppresses everything but error messages. Blah, blah, blah. Hey, look at that. I could say status equals. I literally have to put the word none in there. Okay, that's nice. So we're all learning something today. Maybe this is easier to understand. Hey, look at that. Either way, it works, okay? Turns out you probably want to learn how to do this sort of thing anyway, because it comes up all the time and everything is different. So by throwing away the noise from DD and just taking the binary data from that first block from SDA, which is going to be the MBR, and then dump it out in hex in the usual way, we nice report like that, okay? So here's what's in there right now. Okay, what do we got? From 0 to somewhere around here in hex, we see a bunch of junk down there. This is presumably what a standard MS-DOS boot up code looks like at the beginning of the MBR. These are probably a few instructions that diddle around with the BIOS and tell the BIOS to load an operating system out of the first partition or something like that. Or it's some code that simply says, I don't know what to do. Okay, I don't know. But this is basically an IBM PC type of thing, which is a very standard bunch of code to put in the beginning of your boot record. We don't care what's in there. That's the key here. All right. Then down here near the end, here's your 55AA. So now we have a real MBR down there. And look at these addresses down here in hex. There's some garbage right here at 1B8 into the dump. If I put in, what is it, man, hex dump. There's a command in here that says don't suppress. Oh, there we go. Verbose or something. V. Yeah. Okay, so if I run the same command, look what's happening here first. What this is doing is it's saying, look, here's all these lines have data in them, and each line is unique, and you'd want to see this. And then you get to this at address hex 50. It turns out that 50, 60, 70, 80, tons of lines that it would otherwise print on the screen are all the same. So it puts an asterisk in here, okay, until you get to here. And it says, aha, yeah, there's some data in here. The next line on the screen is all zeros, and the next one, and the next one, and the next one, and the next one, and then this one is new and unique and different, so it shows it out, right? This is normally very desirable. But right now, it's a little bit annoying, so let's dump it all out and not suppress all these zeros, okay? Why? Because what I really want to do is make sure that we see, in no uncertain terms, these 4 partition table entries, okay? Remember in the Wikipedia page, there are 4 entries, and then there's this marker. Each entry, by the way, is 16 bytes long. We go back over here. All right. Yeah. Each entry, well, if we scroll up here, it'll show you where they start. The first one starts at B01BE, CE, DE, EE, and so on, right? At 01FE and FF is our signature here, okay? So here's your 1FE and FF, right? So this is the 4th, the 3rd, the 2nd, and the first partition table entry. Every one of them is currently set to 0, which makes a certain amount of sense if you think about it, because we didn't create any table entries in there, okay? So as it is right now, where's the little entry here? It says, okay, status of the drive. Okay, they only accept 80. 0 means it is not active, okay? 1 through 7F means they're invalid. And this is the kind of thing that would be nice to put that in there. We're going to go ahead and leave 0 in there for now. Okay, let's go and run the command again. If I go find it and cut and paste it, and rerun the editor. You can go ahead and do a print again, and again, yes, because it's not just all zeros. We're going to create one partition, all right? So we're going to say make, we already did this. You don't need to do it again. I suppose you could. Well, we're going to make one that's 128 megs starting at 1 meg. Okay, and then we can print it out again, and we can see that this matches what we see up here, okay? So it's at 1049 for 135, 1049, 135, blah, blah, blah. And it's the entry number 1. We type quit. We go back up here and hex dump it again. And we can see there's partition entry 4, 3, 2. And now partition entry number 1 has some data in it, where before it was all just zeros, as you saw up here after this 2E, blah, 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 7F60. Here it is again, and here's our first entry, okay? So what do we remember from reading the doc? This is the number of blocks in the partition. This is the block number where the partition starts. These are little endian 32-bit values, so 00000800. In hex, 800 times 512 bytes equals 1 megabyte, all right? And this number here oops, that's not where it starts here, is going to be your 128 megabytes, right? So that number is 4,000 times 512 bytes is going to be your 128 megs, all right? So there's our partition table entry that we really wanted to have in there. What is its type, right? So its type is 0. So it starts with double zeros, and then it's got the 20, 21, blah, 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 blah. Those are going to be your cylinder head and whatever it is, CHS value, right? So this is the second byte for 3 bytes, and then it's got, I don't know, this is how the head and the cylinders and all that junk are defined. Then there's a partition type, which is 4 bytes into the entry. So that is going to be where? The first one is here, 2. Well, that's byte numbers, offset 0, 1, 2, 3, 4. So what we really have is an 83 in hex in there, okay? So if we look up what an 83 is by maybe clicking on this, let's look and see if we got an 83. Unfortunately, that's in hex, and I wonder if these are in decimal. Oh, no, they're not. Beautiful. Okay, so what's an 83? It'll probably say it's Linux. There it is, 83. File system, Linux. Blah, blah, blah. Any native Linux file system, C93, and blah, blah, blah. It corresponds with that, and yada, yada, yada. So this is why we have a Linux file system, mainly because that's what it set it to. And it's LBA mode, so we have all the right values. Okay, this is super duper critical. We know where the block range is on the SD card where we now want to put all of our files. Now, we scroll down on this page a little bit more, and there's, again, I should put the -V in here. And then this is me walking through what we just did, and this will be the same exact thing. Why didn't I scroll down? I don't know. Yeah, I'm citing the source of my information. Why not? Okay, so and I do the math here, and I show, oh, look, this is your 128 megabytes, and this here is this, which is equal to the 1 megabyte where it starts. So it starts from 1 through 129. Because I want a total of 128 in that partition, okay? And I put a note in here. Yeah, it would be nice if this somehow could be set to this is not valid and it's experimental, right? The fact that it's not bootable and inactive will make it a little more friendly with your desktop OS if you plug it in there. Okay, so what happened when we did that? Linux knows we were diddling with SDA. If we now type ls-al on all the SDA files, there's an SDA and there's an SDA1. Now the SDA is the same as it was before. This is a logical drive, a logical device from the perspective of Linux, right? That represents the contents of the entire SD card starting at block 0 through block N, however many there are on the whole card, okay? Now it does us this favor, it creates another device called SDA1. This is the view of every block on the SD card that is a element of partition number 1 here, okay? The first one in the partition table. So they've done us a bit of a favor. We don't have to, keep in mind, we don't have to remember exactly where the blocks are that represent partition 1 because the table does it for us. If we create another partition that covers another part of the SD card, there would be an SDA2, an SDA3, an SDA4, each of which represent up to those 4 partition table entries in the MBR. All right, so let's, what do we got here? Yeah, and that's what I say here. It's the entire raw drive is still SDA, and SDA1 is only that first partition number 1. Now, we can do anything we want, right? We're voiding our warranty. We don't care. It doesn't have to have a file system in there. I mean, only normal people put file systems in their SD cards. We can just write raw text right in to the blocks inside the partition number 1 of our SD card. Now, I wrote this because I wanted to make sure that we're compatible with the block size of the drive. And I've been playing around with this earlier today, so we have to be careful. I'm going to go back up here, and what I'm going to do, so that we all have the same results, first I'm going to draw dev0 into This is critical. SDA1. Okay, if I run, oopsie. This is why you don't run this on your desktop. I just blew it. I just blew away the partition table. I didn't realize a carriage return would be part of that paste when I copied and pasted it. And as you can see, my partition went bye-bye. So this is a great example. Let me clear out a few more blocks on the drive so that we have a big clean slate. I wrote so many blocks in this time as to make sure that I covered and zeroed out a bunch of the blocks that are inside the partition that's on there as well, because earlier today I already had data in there and I didn't want to confuse the situation. Now, what did it say it did here? It moved in that many bytes. That's not really a lot, is it? Let's do this again and put in 10,000 instead of that. All right, it'll take a little longer. Now it wrote in 5 megabytes, okay? When we create our partition table, remember, our file system will start at the 1 megabyte line in the SD card. So I've zeroed out so much that I've zeroed out the first part of what will be, when we're done, the beginning of the partition that we're going to write the hello world into. Okay, so we get to go back here now and redo our partition. Yeah, that was just funny. I'm sorry. Always a good time. What do we want to do if I print it again? And we'll see it's empty again. And we're going to make a MS-DOS partition. Then we're going to put one in there. Fill it in, and we don't need to see it again. We're doing the same thing we did before. Let's be careful with our command history so I don't delete it again. Why does this not? Maybe I must have copied too much, as I expected it to not put a carriage return in there earlier today. So here it is. I've dumped it out again. We can see the partition table entry data in there. That's fine. That all jives. We can see that the partition itself would have come back. If we do this, we got it back again. Now let's do this and not screw it up this time. So we're going to write hello world into the card, okay? And we're going to write it into the first block, into blocks, starting at the beginning of this partition number 1. All right, so if I go hello world and I put it on the card and I say write it in 5 12-byte blocks, thank you very much. It says it only did 13 bytes because that's all there is in here, okay? Now, this key, where did it go? So let's say we say I want to see, like we did before, I want to dump out the whole thing, starting at physical block number 0, the whole SD card. So what I'm going to do is I'm going to say dump out SDA, starting with the MBR, dump out 512 blocks, and dump a lot of them, throw away the noise, and then dump it out. Now, I'm not going to put the -v in there, because an enormous amount of lines of output will be all zeros right now, okay? So I'm going to dump out the entire raw disk up to 9,000 blocks, all right? Now look what we got here. There's the hello world, all right? So where is hello world? It's there. This is hexadecimal bytes from the perspective of DD, and one with, what is this, 5 zeros after it, is 1 megabyte. In decimal is, 100K in hex is 1 meg in decimal. It's just a coincidence, okay? So you can clearly see the hello world went onto the drive. It did not go here into, byte number 0 in block 0 on the physical drive, because I wrote it into dev SDA1. And dev SDA1, as defined in this partition table entry right here, starts at address 0000800, that block number, okay, times 512 bytes each, then convert it back into hex as this value here, okay, and that's where this thing went. All right, so clearly we're filling it in the right spot. Now, if I want to, I can also do this. And again, you can be very careful with this stuff. And this time I'm going to write it into SDA instead of SDA1. All right? Now, let's rerun this again. Look what happens. Now I got a hello world up here. and I just blew away part of the very first block on the SD card, because that's what SDA is. All right, again, reconfirming 10 times more than should be necessary, but just to make sure everybody understands what's going on. So SDA is the whole drive starting with block 0. SDA 1 are only those blocks that comprise partition number 1, starting at the beginning of partition number 1. Okay, now you can even say cat dev, well, I'd have to do this as root, because regular users can't just open and diddle around with the drives. 1, right? So what is this thing going to do? It's going to take the text that's in this file from the perspective of cat, and this is the whole point of why devices work the way they do on Unix systems. Devices, files, whatever, they all work the same way. Therefore, any command that can open a file can open up anything. I can just cat this to the screen and see, well, there's all the garbage that's in there. You saw it started with that. Let's go in here and type in, well, actually, you could use cat if you want to. We could also get rid of the hex dump, all right? If we said read from SDA1, block size 512, count equals 1, and don't do anything, it's going to print to the screen the raw characters rather than pipe them into hex dump and give them to me in hex. So I can just see the hello world right there. So, I mean, if I don't want to create a file system that has, directories and everything else, in theory, I can just treat the partition on the SD card as a single file. You can't rename it or anything. It happens to be called this. Entire contents of SDA1. I could just put tons of whatever I want in there. And that's what we're going to do. What we're going to do is write a program that essentially prints out, again, I'm air quoting in the studio, you can't see, the bytes that will comprise, the CP/M operating system, the BIOS, and the file system for CP/M, all in one big wad, and we're going to just save it in dev SDA1 like it would be any other file in the Linux Unix environment. Okay. Then I'm going to put in my retro board. We're going to take the firmware that we saw earlier. Whatever, which is up here. It's in the, well, actually, I'll click around and find it. It's the thing we started with, right? The thing that reads in the first 16K from the first partition right now. Okay, it has, this is the demonstration I just did, right? Right now it has the string hello world in it. If we wrote the flash with the boot up code, and we put this card in there right now, the retro board would load hello world into memory, and then it will jump here and try and execute whatever that means, right? These would be treated as instruction opcodes and stuff like that, all right? So here are some variants of how to dump it out and all this other fun stuff. What else do we got from the perspective, how do the mappings and the addresses all work and stuff like that? Now, if I wanted to, I could save the code in this hello program in there right now. I could burn the firmware that reads this thing in, and I could boot off the card if I wanted to, all right? And why don't we go ahead and try that just for fun. All right, so that's in the boot directory, right? I can do a make world, make sure it's all compiled and ready to go. And I'm on my Pi. If I then say cat the readme file, I always keep these handy little cut and pasters in here. Now I have also in my home directory, I have checked out, I've cloned the programmer repo and the hardware repo, the Z80 hardware repo and the Z80 CP/M repo. So I can just reach up and around by running the flash programmer, which I always leave compiled in there for times just like this. And I can program my flash card. This has nothing to do with the SD card, mind you. Remember, this is plugged into my retro board. So I'm going to program the retro board flash to read in. This is the program that we just looked at a minute ago. It's going to read in the first partition table entry and then try to execute it. And this, oops, if in that partition, jeez, I can't do anything. Read me, please. And if I put this into the partition, that firmware will boot this thing up, okay? And this is actually the structure that we will use to run the real operating system. Now, next time, we'll play around with these when we're debugging our SD card driver. But right now, let's go ahead and finish this off, and then come back in and look at how it all works later on. So what is this one going to do? This is writing now this hello binary, the binary executable out of the assembler here, out to partition number 1. Okay, we're not blowing away the whole card again. And again, we saw this earlier. This is the hello ASM. Now, it doesn't run out of the flash. You're not going to see the flash startup or anything else going on in there. This simply expects that the machine is already started and that the serial I/O ports have already been configured and the CTC is running, so we have the right bit rates and all this other fun stuff. And it's just going to go into this loop, and it's going to print hello from the SD card. Now, so it doesn't just spew too fast. I put an endless, almost endless loop in here. I count up to 64K, and then I come up here and print it again and again and again and again. All right? Now, each time through this loop, what do I do here? I have a register called DE. I increment DE. I have a counter. All right? So it's going to count 1, 2, 3, 4, 5, 6, 7 while it's going. Okay? I do that because if it's scrolling real fast and it's printing the same thing over and over again, you can never really tell it's updating the screen. So the only thing this does is print something unique one line at a time and puts a little bit of a loop in there, wasting time, okay? So cat out the README file again. If I do this, I'm writing it into the first partition. If I did this down here, remember this zeroes out the first, it throws away the MBR. If I do this, I will copy hello binary into the MBR. This is the block number 0 on the whole drive. This would put it in block number 0 on just the partition number 1. For now, this is the one we want to do, okay? So I'll go ahead and do that. Usually you want to type sync before you unplug a SD card. I believe it is automatically synced in this scenario anyway, because there's no real file system on it and it's not helping us, okay? Point being, if you forget to do it, it's probably not the end of the world. All right, so the first thing we're going to do is just reach over and press reset on the retro board with no SD card in it at all. And this is what the flash boot ROM code is supposed to do, because there's no SD card. So as you could see, we talked about this earlier, it says I can't read a card, and it returns and it says it's halting. So that tests that. Now we put the card back in, press reset, and we see it boots up. It obviously read the SD card, and it's obviously running our hello program, and it's counting tick, 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 tick. Now, at this point, I hope that you have a bird's eye view of how this thing works, the whole thing about the master boot record and the partitions and the block numbers. They're all 512 bytes each and all this other fun stuff, because you need to understand all this before we really talk about the driver, because the driver is geared around all this same basic fundamental facts, all right? And in the fact that SD cards have all these different crazy options, when we look at the documentation and all the commands, and why the heck do we got to do this and that and the other thing, it's because the SD cards have so many variations, and we want to thread a certain needle just right to get it to boot up, go in the right mode, run SPI, get the blocks we want, and run our operating system and interact with the card as a regular storage medium. All right? So thanks for watching. I'll see you next time.